What really excites me is that it is an opportunity for us at onsemi and throughout the silicon carbide supply world to provide technologies that make the planet a better place. It's to increase the sustainability, more efficiency, and also drive these megatrends towards electrification. All of these things really will enable us to leave a planet behind for our children and posterity that we can be. So very high level. That layer that I just told you about before, we grow this epitaxial layer, and that's to block the voltage. Very simply, this layer on silicon carbide is for 1200 volt device, for example, which is powering a lot of the electric vehicles that are getting designed today. It's about 10 microns. Okay, so that's 10 to the minus 6 meters. It's very, very small. By comparison, that same 1200 volts, if you were to do it in silicon, roughly 100 microns. So it's a 10x reduction in that thickness of that layer. And what that does is it allows the silicon carbide to very efficiently handle the power, both in the on state and the off state, as it's being put into these systems that require 1200 volt devices. Silicon obviously can fit in those sockets as well, but you will get a tremendous amount of losses. And in applications such as traction inverter, for example, what that means is you have to oversize your battery. So you need the battery to be big enough to supply all the power you need to propel the vehicle. And now you also need to add more battery to take care of all the losses that the silicon would generate. So very simply, by going to silicon carbide, that semiconductor loss part of it gets dramatically reduced. And in the case of traction inverters for electric vehicles. So the challenge really comes down to being able to grow the crystal. This is a very challenging part of this entire manufacturing. As I explained before, it's very challenging because the temperatures are so hot. And then if you do not control gradients and the internal design of this very carefully, you can easily get to crystal defects. So you can go in and make this. You can produce pucks like that. But the real challenge there is, can you make that high enough quality to be able to run through your manufacturing? That's really where the challenge is. And this is not something that is, it's not a commoditized technology. It's very selective. We acquired GT Advanced Technologies because their core competency is based on the equipment itself. So you can imagine there's both the thought of how do I design this, but then how do you actually implement this in equipment? And that's what our colleagues in Hudson are very, very good at. Their core competency is how to make this equipment. That's step one. They spend a lot of time improving and tweaking the process. That's step two. Those are two very difficult steps that does create a bit of a barrier of getting into this technology for everyone. Not to say it won't happen, but it'll be much slower than what you've observed in silicon because the process there is just much easier to do.